Okay, off we go. Let's get started. Let's talk a little bit about today, and then we'll talk about next week. Just as a reminder, we're working our way through our third section on various aspects of human cognition that bear on HCI. We finished last time by talking about mental models, about how humans are able to create mental models and what they're for, which is primarily for prediction. When a user sits down with your ASL educational software at the end of the semester, they're going to wave the hand over the device, see what sort of visualizations they get back, and build up gradually an understanding or a mental model of what your system can and can't do. And if their predictions that come from that mental model don't match up with what your system tends to show them, they're going to be frustrated or what have you. So we talked about mental models last time. I showed you an example of a robot I worked on a few years back where that robot also made mental models and used them to make predictions. That aspect of human cognition is pretty well understood. Today we're going to talk in lecture 11 and 12 about other aspects of human cognition which are not as well understood. They seem obvious to us, memory, attention, and perception, but when you start to dig down and get into the details about what these aspects of cognition really are, a little bit harder to pin down. Next week on Tuesday, next week, Tuesday and Thursday, I will not be here. I'll be traveling for a conference. You will have two guest speakers next week. The first one is Sam Kriegman. He's a PhD student in my lab, and he's going to deliver the 13th and final lecture in this four-part series on cognitive psychology. And Sam is going to be telling you about affect, which is psychology's fancy word for emotion. How might an interactive technology recognize emotion in a user, and how might we build emotions into our machines, or at least machines that give the impression of having emotions, and why the heck would we ever want to do such a thing? Sam will tell you a little bit about that next Tuesday. We're going to talk about Deliverable 6 in a moment, and Deliverable 6 is due next Wednesday night at 11:59 p.m. Just as a reminder, we pushed back by 2 days the assignment and due dates for the deliverables, which gave Jack, the TA, time from Monday night until early this morning to stitch together all of your data sets into one big data set, which we'll talk about in a moment, which is now available to you in Deliverable 6. So you'll have, starting this morning until next Wednesday night, to work on Deliverable 6. Next Thursday, you'll have a second guest speaker. This is Nick Cheney. Nick was actually an undergraduate here, went off to do his graduate work, and has now returned here as a new faculty member in the CS department. And Nick is actually going to talk a little bit about his research with robotics and all the different visualizations he's created along the way to visualize what's going on in his robotics research. He also now works in deep learning and reinforcement learning. These are different aspects of machine learning. And he will talk about, again, very briefly, those algorithms, but more importantly, how might we visualize what a deep learner is doing, and use those visualizations to understand where it's working well and where it's not working well. So this will be a bit of a refresher on our discussion about visualizing visual design and visualizing large data sets. A big issue in AI at the moment is what's known as black box and white box AI. So you can have a very powerful AI algorithm that's able to make great predictions, but it is not able to explain to a human how it came to the prediction that it's making. And as we start to deploy AI into the everyday world, that's going to be incredibly important. So there's a big challenge about how do you take a black box AI, black box in the sense that you put your features in and a prediction comes out, but you don't know what's going on inside the box. There is now a lot of work in HCI dedicated to sort of opening the box and turning the black box into a white box. We can see through the box and understand what the machine learning algorithm is doing, or it can communicate to us what it's doing, and most importantly, why it's making the choices that it's making. So Nick's going to tell you a little bit about that on Thursday, and then I will be back the following week when we will start in on our fourth series, fourth theme on this idea of looking outward. Up till now, we've sort of been focusing on the technology itself, but we haven't really talked about situating technology in the real world. What happens as we start to stitch technology into our everyday world? There's a lot of aspects of that that we're going to touch on in the weeks to come. Okay, so that's where we are and where we're going. Let's talk a little bit about Deliverable 6. Here is, as of 2 o'clock this morning, our current state of affairs with all of the data sets. We don't have data sets from everyone yet. As we collect those, we will put them into the data set and we'll refresh the link where you can download them. But for now, to complete Deliverable 6, you don't need everybody's data set. So you're going to be using this data set. I've put some asterisks next to some of the submissions, which just looking at the percent accuracies to me seem like something might not be right. There might be an issue there. So later in Deliverable 6, you're going to gradually start to add other people's data sets into your own. Do not include the ones that have an asterisk for now. As we get those submissions and work with those students, we'll remove the asterisks and clean everything up. And by probably next week, we should have a completely full data set. Okay. Okay, you can have a look at that at your leisure. So what are you going to be doing in Deliverable 6? Well, like you've done in previous deliverables, we're going to bring together things you've been doing in previous deliverables. The first thing is that you're actually going to save out your KNN classifier. So you have that classifier already. You're going to save it out to a file, and then you're going to read it back in to your file that simply just draws the hand. So remember your original file where you were just drawing the skeletal hand. You were capturing a frame, and every time you captured a frame, you would draw to the screen. Now, every time you capture a frame, you're going to draw the hand, and you're going to take the data from that frame, feed it into the KNN algorithm, and the KNN algorithm is going to give you back a single number, and that's an integer between 0 and 9. Which is the KNN algorithm's prediction about are you signing 0, 1, 2, 3, 4, and so on. You may not be signing any digit, but the KNN algorithm is going to try its best to guess which of those 10 digits you're signing. So when you get to the end of Deliverable 6, you're going to be submitting something that looks like this. Here's my Deliverable 6 running. And you'll see the visualization here and the predictions down here. 4, 5. It's not recognizing my 5 there. It's recognizing 5, 6, 7, 8, and 9. Okay, so I am demonstrating here in the deliverable. I'm demonstrating here in my video that I now have a KNN algorithm that's not perfect, made a few mistakes when I was signing. Actually, I made a few mistakes and it was right, but here you go. Humans aren't perfect, and neither are machine learning algorithms. But more or less, it's doing a pretty good job in real time of predicting which of the 9 digits, or which of the 10 digits I'm signing. Okay. Okay, so you work your way through Deliverable 6. When you get to step number 12, there's a link here that points to a zip file which contains everybody's user data. As I mentioned, as we get some remaining data sets in there from the rest of the students, and we clean that up, we'll periodically refresh this link. But for your purposes, it doesn't matter. For now, just use the link that's there. And then as you get to the end of Deliverable 6, what you're going to be asked to do is to pick one other student, and that other student is going to have 4 data sets, right? Train X, train Y, I'm getting it wrong now, train and test for the 2 digits, right? So we've got a total of 4 data sets. You'll read in those 4, which will give you a third, or so it'll give you a third and a fourth digit in addition to your first and second digit. Once you get that working, you'll have a KNN algorithm that recognizes 4 of the 9 digits. You'll go back to the data set, then grab another student's data set that will give you a 5th and 6th digit. Make sure everything's working, and now your KNN algorithm should recognize 6 out of the 10 digits, and keep going until you have all 10 digits done. You don't necessarily need to use everybody's data set as long as you have a KNN algorithm that can do pretty good at recognizing all 10 of the digits that you sign. Sound good? You can read the rest of the details at your leisure. Any questions about that? Okay. Okay, so back to lecture. We're gonna lecture 11 is pretty short. We'll probably get through that and make a good dent in lecture 12 today. So let's switch and talk a little bit now about memory, attention, and perception. And the three different aspects of human cognition. Again, these things are very familiar to us because we're very good at it. Your memory may not be great, but it's probably not too bad. Memory is sometimes used as a noun and sometimes used as a verb. I have a memory of my grandmother, and I also practice memory. I remember things, I memorize things. So when we talk about memory, again, keep in mind this is sort of a vague concept. We generally know what we're talking about, but sometimes we're talking about the thing, the memory, and sometimes we're talking about the process. When it comes to HCI, what we're usually interested in is focusing on recall and recognition, and short and long-term memory, or working and long-term memory. Again, memory itself is a fascinating subject. We could spend a whole course talking about it and focus on just these distinctions and why it matters for HCI. We'll come back to that in a moment. Attention, again, is something that seems pretty obvious. Hopefully, I have most of your attention at the moment. I may not have your attention for the entire lecture. You may find yourself daydreaming from time to time when your attention turns inward, where you may be daydreaming, which we now know is not just an idle process, but you're refining your internal mental models, right? Any inner mental life you have, most of the time it's not just wasted time. You're building up an understanding of self, this lecture, something that happened to you yesterday, last year, what have you. Okay. Then we're going to talk about, the last part of the lecture today is perception, and we're going to distinguish between perception and sensation. So for our purposes in HCI, visual sensation are photons that are falling on your retina. As long as your eyes are open, you don't have much control over that. You passively sense light out there in the world. Once you sense something, however, your brain takes over and actively starts to impose meaning or structure on those raw sensations, and you perceive things. What's important about perception compared to sensation is that it's an active process. It has a motor component. As I perceive the room, my eyes are saccading or jumping around my visual scene and building up a 3D representation, a mental model of the classroom as it is this morning, right? Going from raw photons falling on my retina to building up this mental model. That process from photons or pressure waves arriving at my inner ear is the act of perception is translating that raw sensation into usually ultimately a mental model. Okay, we'll talk about that and why that matters. Like we've talked about before, or like we talked about last time, we're often doing this in an active way to prove and disprove mental models. I think that is student so-and-so in the back, but their face is occluded, so I might move a little bit to prove or disprove my guess about who is actually sitting in the back of the room. Okay, so we're going to talk about these three aspects of human cognition today, but before we do, a little bit of a warning. Thinking about thinking is misleading. This is important for our purposes in cognitive psychology. If you've taken my robotics course, we spend a lot of time talking about this. Clearly, you have memories of various things. You have attention that you can focus outward, or you can turn your attention inward. You perceive the world around you, and so on. They feel like separate things. It's obvious how these three things work. A warning, they might feel like they're happening in one way, but in reality, they may have a very different form. To make this point about thinking is misleading, I'm going to use a very controversial example. I am not trying to convince you whether or not you have free will. Again, that is probably a subject best left for another class or another time. We're going to talk about the Libet experiment in a moment because it's probably the clearest example of how often our thinking about a particular cognitive process, which in this case is free will or choice, if you like, is often misleading. Who has seen or heard of the Libet experiment before? Only a few people. Okay, you're in for a treat. Here we go. It's been around for a while, obviously, in the early 1930s. Libet and some of his colleagues invited some human subjects into the lab. They instrumented them with some electrodes, which are electrographic electrodes. So they're collecting electrical activity that's near the surface of the brain, close to the skull. So EEG doesn't give you a lot of information from the inner parts of the brain, but from the surface. But that's pretty good for our purposes because a lot of human cognition, sort of not the animal part, but the human part, the higher level abstraction like building mental models and prediction and thinking about making a choice, tend to be on the surface of the brain. They implemented human subjects with EEG sensors and EMG, electromyographic sensors on the finger, which sense muscle contraction. So they're going to record electrical activity from the brain and muscle contraction. And they're going to measure both of these signals over a time period. What they asked the human subjects to do is to watch the face of a clock. And on that clock, there was a moving red dot. And they asked the subjects at any time that they wanted to freely choose, I'm going to put free in quotation marks now, to freely choose at any point to decide to move their finger, and at the moment they decide that they should move their finger. So the subjects were asked not to cheat, to think, I'm going to move my finger and then not move my finger. They were asked to be truthful. Now, whether they did or not, it's hard to say. This is one of the issues with the Libet experiment. But we're going to assume for the moment that human subjects played this game honestly. They watched the red dot, and when the red dot reached a certain point, they moved their finger and they reported back to the experimenter exactly what time did they make the decision to move their finger. Pretty straightforward, right? Okay. What they found was that most of the time at which the subjects reported that they decided to move their finger, about 200 milliseconds later, the EMG signal recorded that the finger actually started to move. So it seemed that most of the subjects were reporting things honestly. You make a decision, it takes a little while for that signal to get from the brain to the finger, and 1/5 of a second later, your finger actually moves. Seems pretty straightforward. It turns out that what they found is that for different subjects, they had individual subjects do this multiple times. I forgot to mention that. Every time a subject decided to make this, it might have been at different times, but at those times, for a single subject, there was a particular pattern in the brain that was constant as reported by EEG. So they were using a machine learning algorithm. It was a pretty rudimentary one back in the 1980s. But it was enough for the algorithm to say, listen, subject 3 has played this game 5 times, and every time subject 3 reported that they chose to move their finger, there was a lot of differences across those 5 EEG snapshots, but there was one part that was constant across those 5 EEG snapshots. For another user, they might have played the game 7 times. That user also typically had some part of their brain that was constant, or pattern of the brain that was constant, but which part and what that pattern was obviously differed from one subject to the next. Our fingerprints are all unique, so are our EEG signals. What was important is that they could isolate in the EEG some pattern that was only there when the subject decided to move their finger. The rest of the time, in here and in here, that constant pattern didn't show up. So far, so good? Now, whether that part is the part of the brain that is making the decision, that's impossible to say. All we know is that when they made the decision for individual users, there was this constant pattern. Not so surprising. What was surprising is that for all of these subjects, 300 milliseconds earlier than the time at which they believed they made the decision, there was some other part of their EEG signal that was also constant across every snapshot or every time they played this game. Troubling. Why? Question?
Well, yeah. Humans aren't that good at timing down milliseconds.
They aren't, exactly. So there might have been a problem in the reporting, and they tried to control from that for that. As the best as they know, and people who have replicated this since, as far as we know, the humans made the decision, and they're watching the clock is exactly when that happened. They might have been off by a little bit, but they would have been off by different amounts for different people. So 300 milliseconds might not seem like a lot, a third of a second, but it's enough. It's enough of a lag to be a little bit disconcerting.
Could it be because like you actually have to process the thought of I'm going to move my finger now, whereas usually just move your finger?
Possibly, right? So did it take a while for the decision to actually manifest in your mind, right? You decide at this time, but you're aware of that decision as far as the Libet experiment knows at this time. But Libet and colleagues knew that you made the decision actually a third of a second earlier. So yes, it might have taken a while for it to reach the conscious part of your brain. Question?
Well, it could be the point at which you're deciding to find a point on the clock.
Possibly.
Like it takes mental faculties to read the clock precisely.
That's it.
It might be like, okay, I've got to watch the dot and now.
That's it, possibly. So you can actually play this game without the EG and the EMG, get a normal clock that has a second hand that's moving. It's got to be moving constantly. And just watch the clock and try and relax, and then at a certain point decide to move your finger and note the time on the clock. You may realize that there's a little bit of uncertainty in exactly when you decided, but that uncertainty is probably less than a third of a second. Again, it's a short period of time, but still pretty long. Okay, so again, we could argue back and forth. There are some weaknesses with this approach. It was surprising to the subjects to be told, we know when you're going to make the decision. It's 300 milliseconds earlier than you think you made the decision. So if the decision is happening in your subconscious and you only become aware of it 300 milliseconds later, you don't have any control over your subconscious. It decides and then tells you to move your finger. So also a little bit disconcerting. Okay. Again, I'm not trying to convince you that you don't have free will. One of the interesting things, there's many interesting things about the Libet experiment is that it raises some uncertainty. The subjects before this would have been certain that it was exactly at 2.7 seconds beyond 12 that I made the decision to move my finger, but it was not. It was 2.4 seconds beyond. Yes?
So that wouldn't just be like reflex, like versus subconscious or like conscious?
The reflex over here?
Yeah, like.
So this part is not so controversial, right? This makes sense. I make a decision and I move. You know, it took 200 milliseconds for the signal to get there, plus the time it took for me to actually initiate the movement. It's this part that's challenging. This is all the stuff that's just going on in the brain before any moving of the finger. There's a lot, as you can imagine, there's a lot that's been written about the Libet experiment. If you're interested, go and read it. It shows us that thinking about thinking is misleading, right? I decided I'm going to have a ham sandwich for lunch right now, but maybe I didn't. Maybe my subconscious actually decided 300 milliseconds earlier or an hour earlier. I just wasn't aware of it. Okay. All right, that's enough about free will for now. So let's come back to memory, attention, and perception. Again, just a warning, we're going to talk about these things as they're sort of separate processes, but they're not. They're just manifestations of behavior, so they're only not just separate processes, but they're also highly interdependent. It's hard to isolate any aspect of human cognition from other parts. Obviously, memory is a result of what we perceive. If you don't perceive anything, there's nothing to remember. Changes in attention change our perceptions, which change what we remember. Our memories shape what we perceive. This one is a little bit tricky as well. What other connections exist? What other interdependencies are there between remembering things, perceiving things, and attending to things? How do these three processes influence one another? Yep.
Memory might tell us what to pay attention to.
Absolutely, right? So you may be remembering something, and you may then go back to validate that in the real world, right? So your memories may guide what you perceive. So again, we're going to talk about these as separate things. They're not separate. They're highly interdependent. Okay. As far as we know, there is no separate memory component in the brain. Again, there's a fascinating ongoing argument in the neuroscience literature about the modular nature of the brain. So in this part of the brain, there's memory, there's language, there's perception, there's attention, and there are others that argue that's misleading. The brain doesn't work that way. It doesn't have neat little compartments for the things that we perceive as separate aspects of cognition: memory, perception, and attention. Okay. Just again, something to keep in mind. Let's start with memory, and we're going to play some memory games now. Like optical illusions, we're going to play this game to see what aspects of memory are easy and which are hard, which matter when you go about creating an HCI interface. In order to play this game, you're going to need to have pen and paper. So if you don't have pen and paper on your desk, grab a piece of paper and a pen. I'll give you a minute to get ready. Okay, I'm going to flash up on the screen for 10 seconds a bunch of numbers. Do not write those numbers down. I want you to look at the numbers and memorize as many of the numbers as you can in 10 seconds. And then I'm going to flip to the next slide where I erase the numbers again. And the moment I erase the numbers, write down as many of the numbers as you can, as you remember. All right? Here we go. 3, 2, 1. Okay, go ahead and write down as many as you remember. Thank you. Thank you.
Only the ones that were like certain you remember?
All the ones you can remember. Oh, the ones that you're certain to remember.
Yeah, okay.
It's up to you.
I got 3.
Okay, I don't see anyone writing anymore. How many got 1 right? That's good. Keep your hand up if you got 2 digits. 3, 4, 5, 6, 7. Some of you have had your coffee this morning. That's good. 8, 9, 10, 11, 12, 13. All right. Well, way to go, Olivia. Okay, very good. Okay. We're going to play it one more time. Different set of numbers. Okay. 3, 2, 1.
10.
Okay, go ahead and write down as many as you remember. All done? Okay. How many have got 1 number right? Keep your hands up. 2 digits. 3, 4, 5, 6, 7, 8, 9. Still quite a few hands at 9, 10, 11, 12, 13. Very good. Okay. You can probably imagine in this game, many of you did better the second time. Some of you might have done better the second time because you figured out the game. But hopefully there's another reason why you did better the second time around, which is chunking the information. If you've ever taken a psychology course, you probably heard about this before. Very hard to remember things when you're presented with a wall of numbers or text. Much easier when the information is structured in a particular way or is chunked in a particular way. This is not only chunking, but also trying to put the information together in a familiar form. Although, again, I realize this slide is a little bit dated. Do people memorize telephone numbers anymore? I don't know if that's even a thing anymore, right? I deliberately didn't put any 802s in there. That would have made things much easier on you, right? Then if I had put some 802s in there, we would have switched the game a little bit. Instead of playing the game of recall, which is just remember as many numbers as possible, you recognize things, and then you don't need to remember the entire thing, right? 802 is not necessarily in your mind 802. You can just remember he put up a Vermont area code. So if he asks me, I know that I got 802 correct. So of course, this is not an exercise about telephone numbers. It's remembering this idea of visual design. When you present information on the screen or auditorially to your user, you want to try and structure that information in a particular way that makes it easier for them to remember it or at least recognize it. So chunking is this idea. It's a very popular idea, been around for a long time in psychology, breaking the information up into manageable chunks. When your users use your ASL educational software, they're going to have to not only try and remember or learn the signs for the first 10 digits of ASL, they're also going to have to learn and remember how to use your system, right? You could write on the screen a whole bunch of text explaining everything, but it might be good to break things down into manageable chunks. And it'll be up to you to decide how you want to do that. Remember in your final project that you're going to be doing user testing and you're going to be measuring user interactions. How long does it take your user to figure out how to play your game and move on to the business of actually learning ASL? It depends on how you feed the information to them, right? You might not only break up the information, but try and present information in a way that is familiar to them. What might be some familiar ways of presenting information in a user interface? Probably not going to rely on telephone numbers in the ASL educational software, but what are some familiar ways you might be able to present information?
Headers and paragraphs.
Headers and paragraphs if we're going to do text. But remember, I'm not going to let you do text. We're going to assume that our users don't necessarily speak English as a first language.
Like an animation showing the user with the hand over the...
Absolutely, right? So demonstrations, do what I do, right? So you see the hand in the screen do something and then it disappears. And that may be a nonverbal cue, do what I just did, right? So the user might realize, aha, this system is trying to teach me how to play this game by doing a little bit of Simon Says. The computer does this, and then I have to do the same thing next, right? That's sort of a memorable thing. I get it. I know what we're doing, and it's probably going to show me just one thing at a time, right? Here's how to center my hand over the device, and then it's going to show me, once I've centered my hand, how do I sign ASL? I might then see a short animation that does this, right? I don't necessarily know what that is, but I know that I'm supposed to do that next. It's breaking down the tutorial, teaching someone how to use your system into bite-sized chunks, and presenting it in a memorable way. We're going to play the imitation game, back and forth. Okay. Okay, again, an example, I mentioned this before. I've tried to present you not with a wall of text in this course, a whole bunch of slide decks that are broken up into themes, which are put together into an entire course, right? I've not only chunked the information in this entire course, but presented it to you, or trying to present it to you in a hierarchical manner. Okay. Okay, another important aspect of memory that matters for us is short-term and long-term memory. When you do user testing at the end of the semester, you're going to get your user to play with your system for a few minutes, and then 2 days later, they're going to come back and continue using your system. You're going to do 2 sets of measurements, the first time they ever use your system and the second time they use your system, and they're going to be relying to some degree on long-term memory. They're going to remember what happened the last time. They could, of course, start from scratch and do the whole tutorial over again, but if you presented information in the right way, they might easily be able to remember it and know what to do the next time around. Okay, so again, In the psychology and neuroscience literature, they often distinguish between short-term and long-term memory, and they talk about them as separate processes. They are probably not. They're just recognizable markers on a continuum of the way in which we remember things. But you've all probably had the experience of working in short-term memory versus long-term memory. Working memory doesn't tend to last longer than a few minutes. I'm not going to do this, I promise, but next week if I asked you to write down the numbers from the memory game, probably wouldn't do a very good job, right? No need to move that into long-term memory. Those numbers are not very important, right? So one of the things we do, or we seem to do, is choose or somehow move important information from short-term into long-term storage, and that process itself is kind of interesting. We talk about long-term memory or long-term storage. There's an interesting question about how much long-term storage do you actually have? How much could you actually remember? Nobody knows, but it turns out, as far as we can tell, that it's more or less unlimited. So there's an interesting calculation you can do, which is the human brain is typically made up of 10 to the 11 neurons and 10 to the 14 synapses. Let's imagine that you live for 100 years. So imagine you live for 100 years. Each year is made up of 365 days. Each day is made up of 24 hours. Each hour is made up of 60 minutes. And every minute is made up of 60 seconds. So if you are lucky to live to the ripe old age of 100, you will have experienced in your lifetime 3 times 1, 2, 3, 4, 5, 6, 7, 8, 9, 3.1 times 10 to the 9 seconds. You're asleep for about a third of those, so you could cut off 1,000,000. Let's say 2.1 times 10 to the 9. You have 10 to the 14 synapses, and 10 to the 9, more or less, 10 to the 9 seconds of waking experience. If your brain were to dedicate, 5 orders of magnitude, 10,000 or 100,000 synapses to recording a snapshot of every second of your waking life, you could store, in theory, every waking moment of your life. At the end of your life, while you're lying on your deathbed when you're 100 years old, you could recount every second of your waking experience, in theory. Right? Again, this is a little bit of very hand-wavy.
Are there people that do have that?
There are people that have eidetic memory, which is where a lot of the experiments come from that suggest, as far as we know, it's unlimited. Now, do you need 10,000 synapses or 100,000 synapses to store the perceptions from 1 second of waking memory? No one has any idea. But that's a good amount of information to be stored. It may be possible.
What would that translate into, like, bits?
No one knows, right? How many bits of information can a synapse store? Actually, there are people that try and tackle that question. Not easy to say, but whatever it is, it's a lot. Right? Okay. Interesting to think about. I don't know about you, but I don't feel like I have unlimited long-term storage, but you have a lot. You have a lot. Okay. So again, there's no clear, real dividing line between these two types of memory. But you've probably all heard these strategies for how to remember things and translate short-term into long-term memory. You'll notice if you think about these tips and tricks, they actually rely on some of the things that we've already talked about, which is that memory is an active process, right? Raw sensation is a passive process. Things just sort of fall on our retinas or inner ear. But if we want to remember things, we need to act upon our raw sensations and perceive them. So you can do things like internally rehearse using your inner voice. If you spent the rest of this lecture telling yourself mentally the numbers that were in the memory game, and then next week I asked you, you'd probably remember more of those numbers. So if you actively speak to yourself internally, you can solidify some of that information. External rehearsal as well. My high school locker, I don't remember what the 3-code combination was on the lock. But if I had that lock in front of me today, I could probably open it just through muscle memory. Right? You probably had that experience. Again, this is probably old-fashioned now, but the old touch-tone phones, sometimes you would know a number where you couldn't say what the numbers were, but you could say, right? So there's something about action which also helps with memory, and sometimes action is more powerful than just mental recall. For some people, it's easier to remember this than it is to memorize 802 ... Okay. The more sensor modalities, the more of your 5 or 6 senses that you can bring to bear on recording an event, the more likely you are to remember it, which is why a lot of your teachers probably told you to actually write things down during lecture, read it aloud to yourself after class, watch the video, write it down again, rewrite it, and so on. And especially rewrite your notes because you restructure the stimulus and you're sort of mixing up the raw perception, the raw sensation, and pulling out or distilling the structure underneath. So sometimes the brain is lazy and will just memorize the shape of the numbers or whatever it is that you wrote down, but if you keep changing it, there's no specific detail for the brain to latch onto except the one constant signal, which is 802. When I wrote this book that I assigned as writing for some of the lectures with my colleague Rolf Pfeiffer, the editor asked us to go looking for typos, and it turns out when you write a full-length book, you can have the most high-powered spell checker and grammatical system you want. There are still certain grammatical errors and spelling mistakes that will get through. So they gave us a little bit of a trick, which turned out to be quite helpful, which was to print the entire draft of the manuscript. I then took the last page of the manuscript and I read out loud the last sentence of the book on the last page. As I was reading it out loud, my colleague, Professor Pfeiffer, was at the word processor and reading the words on the screen in the word processor as I read them out loud. Then I read the second last sentence of the book, third last sentence of the book, and so on. So you can probably imagine it was an incredibly painful process to go through. Why did our editors ask us to go through this incredibly painful process?
It forces you to actually really just pay attention to what you wrote.
It forces you to pay attention to what you wrote. You can again play this game yourself. Take your notes and read it from the bottom upward, and you will find all sorts of spelling mistakes and grammatical errors and things that are vague, because when you read it forward, what happens?
Start to expect to read certain things.
You expect or predict to see certain things, right? The brain is a prediction machine, which 99.9% of the time is a good thing for us, but 0.1% of the time it's not helpful, like when you're trying to proofread some text, right? The quick brown fox, ... Most of us would fill in jumped, whether the word jumped was there or not. Your brain is so good at making predictions, it'll make the predictions and say, yeah, I'm pretty sure it's there, let's move on, right? You can break that process. The brain, when it gets lazy, that's all it does is make predictions. So how do you stop it from making predictions? Restructure the stimulus. Mix things around so the brain is actually confused and has to attend, which we're going to talk about in a moment, has to pay closer attention to the actual stimulus. Okay. We can break memory down into short-term and long-term, and we can also talk about recognition and recall. You may recall, we talked about this already when we were talking about user interfaces. It's much easier to recognize something than recall it. You probably all had the experience where you say, I can't remember that word, or I can't remember where I saw that tweet, but I know it when I see it. If you show me a bunch of tweets or a bunch of words or a bunch of images, I'll say, that was the one. That's the one I was trying to tell you about. I may not be able to call it up from recall and tell you exactly what it is, but I can tell you when I see it. It's much easier. One of the things that's important in HCI is to make things easier on your user. We don't want to tire them out and frustrate them. You would like your user to spend as little cognitive effort learning how to use your educational software and save all their cognitive effort for actually learning ASL, right? So maybe we can rely on recognition rather than recall, which was the basic idea behind the initial graphical user interfaces. Before that, all you had was a blinking cursor and you had to remember all of the commands to type into a computer. A GUI presents information where you just sort of have to look, visually search for things, and recognize things. So if that sounds so great, why don't we all rely on WIMP interfaces? Windows, icons, menus, and pointers. Some of us, myself included, still work at the command line. Why?
Recall is faster than recognition.
Recall is faster, right? Recognition requires you to scan the screen and find what you're looking for, right? So in order to recognize things, we're going to have to show you things. And remember our discussion about visual design. We want to maximize the data to ink ratio. Ink is on the denominator, meaning we want to use as little ink as possible. If you go back and look at the history of GUIs, they used to have flashing icons, and the icons would move around and try and grab your attention. There was a lot of junk on the screen. Most modern GUIs have tried to remove as much as possible and present a clean interface. The minimum amount of ink needed for the user to recognize what they need, what they're looking for. Okay, and then also, depending on the user, it requires some intelligence to decide what to present, right? Pop-ups show up because the operating system is inferring that you want more information. It may be right or it may be wrong. Okay. So again, just an aspect of memory here, a difference between recall and recognition and how that influences HCI design. That's what we're looking for in these 4 lectures, is the connection between aspects of psychology and how that influences the design of interfaces. Okay, let's switch our attention and talk about attention now. Again, this one is kind of interesting because the psychology literature has greatly changed the way they describe this phenomenon. It's a very poorly understood cognitive process. It feels like it should be an easy process to understand, right? You're attending right now. Hopefully most of you are attending to my voice or visually attending to the slide. Some of you may be daydreaming. Hopefully you come back to reality and carry on together with the lecture. It seems obvious what attention is, right? It's this sort of beam that's out there, this searchlight that you're wiping across your environment or perhaps turning inward. So not surprisingly, the oldest model of this in psychology matches, the earliest descriptions of attention match what it feels like to attend to things, right? Must be obvious. It feels like this, so that's what's happening. Remember our discussion about libid and free will. We can focus on one thing at a time and everything else is in darkness unless we move that searchlight and attend to something else in our external environment or within. Not surprisingly, when computers came along, the metaphor that psychologists used to describe attention became more like processing power. You have a certain amount of attentional power, and some people may have more attentional power than others. You may also be able to train to improve your attentional power. And you can then decide how to distribute that attentional power to different things. You can't attend to 5 different things in parallel, but you may be attending 90% to the actual content of this lecture and 10% guessing about how many minutes we have left in lecture, right? Maybe something like that. Maybe you may also be attending to something else. It gets harder when you get to 3 or 4. But this idea that we're attending to one thing 100% all the time also doesn't quite seem right. Okay. However, that implies that attention has this quantifiable capacity. 90% to this, 10% to that, which seems again like a bit of an oversimplification. Again, we'll just think about that for now. We'll put that aside. What's important for us in HCI is top-down and bottom-up attention, right? So at the moment, hopefully, you're practicing controlled top-down attention. You are trying to attend to the content of this course. And university classrooms are designed to try and remove distractions so that you can do so. However, if there is a distraction, it becomes hard to ignore it and pay attention to the content of the lecture, right? So that's bottom-up processing. There is something that's happening in the environment that keeps pulling your searchlight. It keeps pulling some of your attentional power to it, and you can try and fight against it. It's a hard thing to do, and as you probably just experienced, it becomes pretty annoying pretty quickly, right? Very important when we're designing an interface. If your user gets into the flow of actually starting to learn some ASL digits, and then you flash up a message about other things they might be able to do with your system, pretty annoying, right? Or you put up a flashing icon in the top right of the screen, they attend to that. Some of you are having a hard time not paying attention to the yellow truck out the window, right? Happens all the time. Okay. Okay. So again, your attention can be switched internally. You make a choice to attend to something else. And unfortunately, the human brain isn't perfect. Sometimes things happen outside that makes it hard to not pay attention to them. And my little GIF in the top right isn't working, but usually it'll switch about every 10 seconds. So as we work our way through the slide, if this is working, every time that GIF changes or animates a little bit, your eyes saccade to that and then hopefully come back to what we're talking about. Okay, so some external stimuli are better at this than others at grabbing your attention. Things that move capture your attention. You've probably all been in a classroom where someone in the front row is watching YouTube and you couldn't help watch what was on their screen. Things that move tend to grab your attention. Things that are still and then intermittently start moving or make a sound intermittently, that is, again, very hard to not pay attention to. So you need to pay attention to all those things that are happening on the screen or in your interface that may or may not be distracting your user. The strength of a switching stimulus, the ability of something to grab your attention away from something else, depends, as everything does in this class, on external stimuli. So if you write some text on the screen and there's some particular information you want your user to pay attention to, you may change the color, change the font, underline things. In the old days, there used to be beautiful websites that were written in all sorts of different colored fonts and different sizes, and so on. If there's lots of things that are changing or different, then your switching stimuli has to work a lot harder to stand out from the crowd and capture your attention. So a lot of early interfaces got into this unfortunate vicious cycle where they were not maximizing the data-to-ink ratio. They were splashing a lot of different colored ink on the screen, making these fancy pictures and animations, because in the old days of web design, it was cool that you could just do this at all. Remember, in HCI, we're trying to resist the temptation to just do something because we can do it, right? Better to present something that's a little bit more conservative, a little bit more low-key, and then if you need the user's attention somewhere, you don't need to exert a lot of effort to capture their attention. Okay. So attention and distraction obviously are either sides of the same coin. Okay, we're going to move on to perception now, and in order to understand perception, we're going to play another cognitive game here. As I mentioned, perception is an active process. So I'm going to show you an image in a moment, and you're going to perform this active process of perception. In this picture, there's going to be some raw sensation that's going to fall on your retina, and the answer, the thing you're looking for, is in plain sight. It's right there, but it's going to be hard to find. You're going to have to instead perceive. Where's the F? Hands up when you found it. Okay, all right, didn't take that long. Now I forget where it is. There it is. Okay. To take 1 second, 2 seconds, not too long, right? 2 seconds, okay. And play exactly the same game again. Find the F. Found it. Okay. So again, not the hardest game in the world, takes a couple seconds. I made it difficult on purpose. What did I do to make this game a little bit harder? There would have been lots of ways to present this where you would have seen it immediately, right?
You smushed it all together.
I smushed it all together, but I smushed it all together in two different ways. Why? So if you go back and play this game at your leisure, right, you are searching for the letter F, but your eyes are not saccading in a random way. Remember our discussion about the Necker cube, right? The way that you scan the Necker cube, you're trying to prove and disprove mental models. When we perform perception, we're often bringing to bear our experiences from other similar tasks. why did I smush things together in rows here, but hide the F down in the bottom row?
Well, the way I think of it is that when you try to scan it, you're doing it left to right, and your brain kind of fills in that missing gap.
That's true, right? So because they're smushed in rows, like the game with the telephone numbers, this is suggesting something familiar to you, right? Lines of text, which normally if you're an English speaker, you read from top left to top right, next row, next row, next row. If I had put the F here, you would have found it immediately, right? So I designed this little interface here, this little picture. I designed it in such a way, which was the worst way I could have designed it for what your goal was, which was to find the F. So this is a bad illustration, right? Because it's going against what you're trying to do. I'm actually making things harder on you rather than easier.
Well, I actually found this one easier.
Okay, how come?
Because the difference between an E and an F is just that small line.
Yep.
And so I'm sort of looking for that white space.
Aha.
The other one, there's a lot more white space. It's harder to find.
Very good point, right? So we're going to talk about that in a few minutes when we talk about Gestalt perception. Gestalt is sort of the idea that the whole is more than the sum of its parts. So for most of you, as you start to perceive the scene, you're not seeing little dashes at the bottom of the E's. You're seeing more or less one solid line, and you may or may not have been consciously aware of that. But there's a good hack. If you're looking for an F, you know, it doesn't have that little crosshatch at the bottom. So if you just look at this horizontal line and this horizontal line, you're looking for the little gap, right? The little space. So in a way, I also made things easier by smushing things together. Here, again, as a native English speaker, your brain might kind of want to read from top left to top right. How many of you scanned top left, bottom left? And then next column, next column, next column? Some people, kind of. Usually this one's kind of hard. You kind of jump around. I should have probably made it more clearly columns rather than rows. If I had designed this in a way that more forcibly forced you to perceive this as columns, again, as native English speakers, even though they're columns, you'd probably work from left to right, and it would take you a while to get here, right? So when your user is interacting with your system, they are performing this visual search thing. Where is the exit? Where is the next level? What do I have to do next? You want to try and design things to make things easier on them rather than harder. There's a lot of interesting work in HCI using eye tracking software. So you wear something like Google Glass, which has an inward-facing camera that's looking at the eye and looking at where the retina is relative to the whites of the eye, which tell the system where you're actually looking. So a camera that's sitting on the inside of the glasses looking at the human eye is like the Leap Motion device getting a raw set of pixels. From that, it's outputting a guess as to the angle of the eyes, and from that, where exactly are the users looking on a page of text or on a web page, or where are they looking in a virtual reality set of goggles, and so on. Usually, if you have a more or less normal looking web page, the eye tracking software will note that your eyes start here. They tend to be drawn to images rather than text. People sort of jump from top left, top right, bottom right to the images, and then, assuming they're paying attention, they might go and actually start reading the text. But as you can see in this example, most of the time we don't read, right? So you can learn a lot about how people are visually parsing your interface using eye tracking software. As you would guess, the mother tongue of this person is probably one of the Romance languages. Read from top left to top right, and then the next row, and so on. Okay. Again, memory, attention, and perception are huge phenomena. We could spend a lot of time talking about them. What I've tried to highlight here is, as a good HCI designer, what are you doing? Which is thinking about your users and thinking about them in a very specific way. What is my user doing? How are they going to try and perceive my system? Do I want them to recall, remember, or recognize what they see on the screen? And where and when do I want to try and draw their attention to certain parts of the interface? Okay, so that's lecture 11. Let's switch now to lecture 12, We're going to continue talking about perception, but we're going to focus on a particularly interesting aspect of perception, which is not just that it's active, we're saccading our eyes and moving it around, but that it is also constructive. Given all of the disparate physical phenomena that are falling on our eyes and ears, like photons and pressure waves, we take that disparate information and your brain tries to stitch it into a whole. Sometimes it does a good job at that, sometimes it does a poor job at that, but like prediction, it's doing it all the time. It's hard to force it to not do that. So here are a couple of cartoons. What do you see in A? You see a triangle, right? There's no triangle that's drawn there. What about B? A snake wrapped around a pole. What about C? Spiky ball. And D? Champ, of course, right? Okay, there you go. Obviously, there is no champ, there is no triangle, there is no snake, there is no bar, but they're drawn in a very careful way that your brain has a hard time not seeing it, right? So these examples here are a great example of exactly that your brain is always trying to put together disparate information and make sense of it, right? The raw perception, the raw sensation is patches of black and white. Your brain has a hard time seeing that unless you explicitly pay attention to it. Okay, so we're going to look at a few of these examples from a particular part of psychology known as Gestalt psychology, and we're going to focus on Gestalt perception, which is this idea that for the brain, the whole is more than the sum of the parts, right? What you're really seeing here is a flood of photons, but that's not what it feels like. It feels like you're looking at a spiky ball or champ. Okay. There's a number of these sort of laws, and laws is a very strong word, but again, it points out some of these examples. The first one is this idea of reification, which is a fancy word for nothing becoming something, right? So there is no champ, there is no ball, there's just raw photons, but your brain imposes or brings into being a percept. So a percept is a noun, it's the thing. The thing you see is the spiky ball. It's not there, but according to your brain, it is. Okay. Lots of aspects to perception that we're going to focus on, not just constructive, but also how we construct these things, but the context in which we go about building up perceptions. As always in psychology, there's arguments about how we actually do this, how we go about perceiving things. Richard Gregory, very famous in psychology, focused on the constancies in our worldview. As we move around, the world around us is always changing, but perhaps what the brain is attending to is the small pieces of our external world that are unchanging. And that's how we pull out the perception. On the other hand, J.J. Gibson said the thing that we tend to focus on are changes in the world. As I move, I see all of your heads flow in the opposite direction. Those of you sitting in the back seem to move more slowly than those sitting in the front. I'm attending to the changes to pull out an understanding of what I'm seeing in front of me. Okay. Here's a great example of how your brain focuses on constancies. So nothing's moving in this picture. Tell me about the gray scale in panel A and panel B. Tell me about the color of A and B.
A appears darker, but I assume they're the same shade.
I assume, right? So the front part of your brain, the prefrontal cortex, that knows that I'm trying to play a trick on you, knows that they're not the same color. There's not one that's darker than the other, but the back part of your brain, which is where most of the visual processing happens, insists that A is darker than B. I'm telling you right now, they are exactly the same color, but the back of your brain, like when we did the Necker cube, will insist that that is not true, right? Okay. I'm done torturing you for today. Let's help a little bit. Okay, they're the same color, right? We're all good? It's like the Necker cube, but worse, right? If you look at B while I do this, Your brain will insist that I'm recoloring B from one slide to the next, darkening it and lightening it, right? Okay. Why does your brain think that B is lighter than A?
Because B is surrounded by even darker colors.
That's true. That's true. So is this one, surrounded by darker colors.
We're used to looking at shadows, and something that things in shadow are
Absolutely. So things that are in shadow are obviously objectively darker. They're in shadow. But it's difficult for your brain to deal with all of that changes, right? So when we look at the world around us, things are changing all the time, right? So the light levels in the room this morning, it's a cloudy morning. It's a little bit darker in here than it was on Tuesday morning, but I still see you all more or less as I did Tuesday, right? My brain is constantly correcting for all the sort of external changes that are going on all the time. If you see a red ball in a lighted room, and I darken the room, your brain says it's still a red ball. Your brain knows nothing has changed. The color of that ball is still the same. The early parts of visual processing, the parts that are dealing with the photons, say, oh my gosh, the color of the ball just darkened. But the other parts of your brain, the later parts, know that's not what happened. They're focusing on the constancy. The color of that ball stays the same regardless of how I play with the lights in the room, even though, according to your retina, the color of the ball is changing. It's darkening and lightening. So your brain has had, again, 20 or 30 or 40 years practice of compensating for changes. And so that's what your brain is doing right now. Your brain is telling you that B is dark. The other parts of your brain are lightening B given the fact of the context, of the shadow, right? It keeps lightening it to the point where your brain is convinced that B is lighter than A, right? It's so strong that even when I tell you that your brain is doing it, you cannot shut that circuit off, right? Unless we introduce some additional context that helps, right? So perception is not just an active process, but like a lot of what we've talked about in HCI, it depends on what else is going on in the visual scene. It depends on context. Okay, so we can exploit this aspect of our brain trying to impose constancy. This ball has this particular shade of red, regardless of the light levels around it. We can exploit that fact when we create visual designs. So another Gestalt law of perception is the idea of continuity. Things tend to be constant or unchanging. Our brain tries to remove surface differences and focusing on the underlying constancy. So again, you can probably bet that when I made this slide, I took 5 half circles and rotated them and put them side by side. But for most of us, this looks like a frilly piece of paper or something else. It looks like one thing, right? So there's reification here going on. You tend not to see 5 semicircles, but one long frilly piece of paper. But you also see continuity, right? So this line continues under the bar, above the bar, and under it. This is the idea of perceptual constancy. Again, why might that matter? Well, here's, again, a cartoon example from visual design. We might be trying to present some hierarchical information to our user. We might have 15 things, and we're trying to show not just the 15 things, but how they relate to one another. We could draw them in a tree like this and link them together to tell visually our user how things are connected. But we've used a lot of ink here. And again, I'm using ink in sort of a metaphorical sense. Maybe there's more ink over here, but we've got 29 visual objects over here. And over here, I tried to create a visualization that exploits this fact that you're always trying to see the whole from the sum of the parts, to convince you about how these just 15 things are connected. Did it work? You know how they're connected, I guess. Not quite?
I don't know. I think the other one is a lot more pleasing for my side.
Possibly. So we can argue about that, about which is more aesthetically pleasing. Perhaps with the smaller cubes, it's a little bit easier. For most of us, again, if I hadn't shown you this, if I asked you how close these two objects are to one another, a lot of people would say they're less close to one another than these two objects are to one another. Because they would perceive the fact that this is actually a tree where things are connected, and I'm cheating a little bit by using color. Literally, these two boxes are closer to one another than these two boxes. But by playing around or trying to exploit the fact that you impose the perception of a tree here rather than 15 disconnected objects, you might see that these two things are further apart than these two things. I probably should have left the color off. Might be a little confusing. So again, in visual design, we can exploit the fact that the brain is always trying to see the whole rather than just the parts. Okay. What other kinds of constancies exist in our world? There's dozens of these Gestalt laws. We're just going to touch on a few of them. One is the idea that we tend to group things together conceptually based on similarity and maybe based on, for example, shape. So like when we just played the visual search game with E's and F's, most people here will see 3 rows, even though if you actually measure the distance from the center of this object to this object, it's the same as the distance from this object to this object. Doesn't seem like it. Seems like the circles are closer together. Yep. Sorry? Possibly, right? Maybe it's just easier to count 3 rows than it is 6 columns, possibly. You could play that game by just adding 3 more rows and see whether your brain tells you that there are rows here rather than columns. Our brains tend to focus on complete objects rather than things that are incomplete. So here's another variant of the Necker cube, the 2 faces and the vase. If you relax and look at this, you'll usually go back and forth between 2 faces and a vase. Yes, more or less. If you actually time it out, your brain will tell you more often that it's a vase than that it's 2 faces. There's a slight bias in this oscillation between the vase and the 2 faces because our brains tend to like things that are fully shaped, right? It's very rare to see an object where you don't see the rest of it. You may see part of an object that's included by another object in front, where that the occluding object then provides an implicit closure to the thing that you're looking at. But it's kind of weird for our brain to see part of something and just nothing else. Not the rest of the face, not an occlusion. It doesn't make as much sense to our brains compared to the real world, so we focus on things that are closed, right? So making these slight changes, we can influence how users perceive information in a visualization. It's subtle, but it's definitely there. Shape constancy, we can continue with this. What's the shape of this object? It's an oval, right? All right. You're cheating because you know the answer that I want. Your brain tells you it's a coin, and we all know that a coin is a circle, right? It's a circular cylinder, but raw sensation tells you that it's an oval.
That's kind of like the basketball game.
The basketball game?
Yeah, where the hoop is actually an oval.
Ah.
It's harder to get.
I didn't know about that
You
one.
can't see it from far away.
I'm going to know next year when I go to the fair. Finally, I'm going to win this game. Okay, good. Yes, exactly. Hard to see these things sometimes, right? So again, raw perception is telling you, obviously, this is an oval, but most people will say, well, it's a circle with a little bit of depth. It's a coin, right? We are imposing shape constancy. So in the same way that the red ball has the same brightness of red, regardless of light levels, this is still a circular object, regardless of its orientation. Okay, we got 2 minutes left. Let's switch from the way in which our brain tries to impose constancy on the world. The world around us is always changing, but we're trying to see the constancy that's out there. Our brain, obviously, as we've already seen, also attends to changes and focuses on change as well. So in psychology, you get a lot of arguments where someone says it's X, someone else says it's Y. For most outside observers, it's obviously both, right? Okay. So objects moving faster than others are closer to us. Motion parallax, we've talked about that one before. If you're creating a video game or trying to create a perceptual system where the user actually sees in 3D, then objects further away better move slower. Objects that are moving further away, if there's a horizon line, are not only moving slower, but they are moving slower towards the horizon line, and they tend to be flowing in towards the center of the screen, right? If you face backwards and walk away, or you look in your rear view mirror while you're driving, objects are moving away from you. That's what your brain tells you. And what they're really doing is actually getting smaller and moving slower and moving towards the center of your visual field. What you perceive is very different from the raw sensation. I think we'll leave things there. You have a quiz due tonight. You have 2 guest lecturers next week. Deliverable 6 is due next Wednesday, and I will see you the following week. Thanks very much.